Okay, welcome to this yet another lecture on liquid drop model, and we stopped at this point. Last time we saw that this is the expression which we derived, that all nuclei whose z square upon a is greater than or equal to 53 is a candidate for spontaneous fission. Now the problem is this is a good uh, figure which has been derived from the liquid drop model, but in actual practice the figure is around 44. This is slightly higher, which means all nuclei whose z square upon a is greater than or equal to 44 undergo spontaneous fission or not existing in this universe, because they have undergone spontaneous fission and they don't exist anymore. So you don't find elements whose z square upon a is greater than 44. Now what we are trying to do in today's lecture is we are trying to see if this figure can be refined to this value. This is also a pretty good value, but in actual practice it has been found that it is 44, not 53. So we will be using a slightly different approach, which was suggested by Bohr and Wheeler, and they could arrive at a figure which is closer to 44, which is actually observed in nature. Now that is going to be the objective of our today's presentation. It is a refinement of stability limit against spontaneous fission. We have derived a stability limit in the previous lecture, but we are trying to refine the limit. Now, last time we had seen what stops a nucleus from undergoing spontaneous fission. This is potential barrier. It is the difference in the potential barrier Vc minus Q of the nuclear fission of that particular nucleus. Now this I'm talking about this peak here. If I can call this as some value, which I call it as Vc. Okay. Now this is what is stopping the nucleus from undergoing spontaneous fission. So we're talking about this value here, Vc minus Q. Okay, so this is what is the key here. Now the candidates of the nucleus whose this gap is less are going to be a good candidate for fission. Artificial fission. When I say fission means artificial fission, this means you bombard projectile on the nucleus and create instability, and the fission fragments are able to overcome the potential barrier and they are able to tunnel out. So the whole idea is that the potential barrier is what is stopping the fission fragments from tunneling out, or it's the potential barrier which stops uh, possible spontaneous fission. Of course, they are a candidate, but they don't happen on their own immediately. For example, this diagram gives you a good illustration. You can see that as A increases, the potential barrier is not existing, but as A is decreasing here, you can see that the potential barrier, the difference here increases as A decreases. So for nucleus whose A is less, it becomes all the more difficult to undergo spontaneous fission. And for higher values of A, obviously the one which satisfies this limit, it's got a one, we have to just derive that. In actual practice, it has been found it is 44. Okay, let me write 44 here. For them, this barrier don't exist and they are able to undergo spontaneous fission. So that's the whole idea here. Now, let's understand a slightly different explanation which was suggested by Bohr and Wheeler. Now, this two gentlemen again use the liquid drop model only, but a very simplified explanation which could give you a refined value of the stability limit. Now, what they said is they considered the nucleus and equated it to a liquid drop, just as we have been doing in a liquid drop model. They considered this to be incompressible liquid. Let me write this here, incompressible incompressible. What is incompressible is the volume remains same despite the change in the shape. The volume does not change. So this is incompressible liquid. So they consider the nucleus to be an incompressible liquid where the volume, you can see that the shape can change, but the volume of the drop does not change. Now the idea is, what it says is that a liquid drop, when it is undergoing fission, it undergoes various stages. So you can see that there is instability within the nucleus which distorts its shape from a spherical to a ellipsoid, and again it then changes into a dumbbell shape, and then when there is further stress here, then the dumbbell shape will then result into the two fragments. One more image I can give you, this will give you a better idea. You can see that the here in two dimensional it is circle, but you know that it's a sphere getting converted into ellipsoid, and ellipsoid finally getting distorted to a dumbbell shape. From dumbbell shape there is a distortion. Just a second. Sorry for the interruption. Dumbbell shape. You can see that there is further distortion, and it finally leads to the fission of the nucleus. So they said that the nucleus is undergoing various stages before it actually undergoes a fission, very exactly similar to a way a liquid drop is split into two droplets. Before it splits into two droplets, it undergoes various changes in its shape. Now, when it undergoes various changes in the shape, then the binding energy is also going to be changed. So we are going to be investigating the binding energy. We had seen earlier that the binding energy expression, only two terms actually changes, which is the Coulomb term and the surface term. These are the two terms which changes. We had seen that earlier. The asymmetric term and the volume term does not undergo any change because the volume is not changing in any case, and the asymmetric term is also not changing because of the number of A, which is constant in this various changes in the shape. So let's investigate what is going to be the change in the value of BC and BS, and what are its repercussions because of which it finally leads to fission. Now this is an ellipsoid. You can see this is an ellipsoid. This is a semi-major axis. This is semi-minor axis. Okay, and volume of a prolate ellipsoid. Prolate means here the shape can be different. Now if this is of this shape, this becomes an oblate. Okay, so right now you see the prolate ellipsoid, it becomes AB square is the volume. So now because of this change in the surface, you can see here the distribution of the charge will also change. If this is spherical and if hypothetically the protons are arranged in this fashion, we're talking about the Coulomb term, so we're not considering the distribution of the neutrons. Of course, the protons are distributed in this way. If it's an ellipsoid, then their position will change. So the separation between them R also changes, which will alter the Coulomb term. And the very fact that their shape has changed is also going to alter the surface term. The surface area is going to be higher now. So now we will see, and the Coulomb term will be lower because the Coulomb expression will be lower because the separation has increased. It is 1 upon R dependence. I think all of you know that Coulomb term, as you know, Coulomb expression is directly proportional to square of charges divided by their separation. Okay, so separation is going to be increasing, the Coulomb energy is going to decrease, and the surface area is going to increase, the surface term is going to increase. Now we are considering incompressible fluid. So in an incompressible fluid, the volume is not changing. This is the volume of a sphere, this is the volume of a ellipsoid. So we are equating these two terms here. Now the binding energy term, this can be, we don't have to derive it, you can see it in any textbook. The surface energy is now going to be directly proportional to 4 pi s r square is the sphere. Now you can see this additional term here. Epsilon is the eccentricity. Eccentricity. What is eccentricity is? It tells you by how much amount is the sphere deviating from a spherical shape. So if more the eccentricity, more is going to be the distortion. If less is the eccentricity, then the shape is going to be less distorted. So this is the original shape. Depending on the eccentricity, the distortion can be described. Now when you say that this object has got deviated from a circular shape, then by how much amount, then that is explained with the help of eccentricity, which is the dependent on the values of a and b. You can see that this eccentricity is defined in terms of a and b. So if eccentricity is 0, then a becomes r, and this is 0, then b also becomes r. So it becomes a and b. So these two axes are same. You can see that r is constant. But if epsilon is not 0, then you can know that the a and b values are going to be different. As you know, this is your semi-minor axis and this is the semi-major axis. They are going to be dependent on the eccentricity. So the eccentricity surface connection is defined as this. So if you put the values of a and b here and do a Taylor expansion, you can directly take this expression, and this power will increase, epsilon square, epsilon cube and all that. So for higher orders we are ignoring, so we are only considering the first term here. For higher orders can be ignored, they are going to be insignificant. So if you can see a minus sign here, surface energy is always negative. 4 pi r square 1 plus 2 pi epsilon square. You can see that the surface binding energy has increased because the surface area is increased. Now epsilon is 0, then this again reduced to is directly proportional to 4 pi r square, just as we had discussed during the semi-empirical mass formula. And then if you finally put the constants and all that, this is the expression you're familiar with. This is the up to this is the expression for the surface for a sphere. But moment it is not a sphere, then the additional terms come into the play, and these additional terms are given in the bracket here. So the surface energy is increased. The Coulomb energy, as I said, will decrease, and this Coulomb energy for charges distributed in a spheroid, in a ellipsoid. That problem you can check in any of the electrodynamics book. This expression you can directly take it, and this is the expression for the binding energy of the charge distributed over a ellipsoid. So this is the expression for the binding energy. You can see there is a minus term here. So up to this point, up to this point is the expression for the sphere, and then if it's an ellipsoid, then you have additional terms here, powers of square, cube and all that. Higher order terms are just ignored here, and the binding energy expression has decreased. Now what is happening? It's a competition between the binding energy and the surface. So the fission uh, is going to be possible only when the binding expression becomes greater than equal to the surface term here. So if this happens, then the protons are will split the nucleus because of the Coulomb repulsion. The fission will take place. So we had also seen this two terms coming into the play when we derived the expression for the cube for in the earlier lecture. So these are the two expressions. Here you must be wondering why we are not considering the volume term and the asymmetric term, because they are going to be same. They are not going to be altered in the case of ellipsoid. So we are talking when it undergoes a deformation, and if this is satisfied, if I am using the word if this is greater than or equal to 0, then fission can occur, and the condition which we arrive after we solve the expression, you can put the values of constants here, A, S and AC, and you can check that this is 44. So the idea is they also resorted to the liquid drop model only, but they used a very simplified explanation. The actual liquid drop model gave us a figure of 53, And Bohr and Wheeler, they did not consider the other expressions. They only considered the Coulomb and the surface term. Here they gave a slightly different explanation of the shape getting distorted, oscillation between the spherical shape and the ellipsoid shape and the dumbbell shape. So using that explanation, they could arrive at a figure which is found, which is closer to what is found in nature. So this is the whole idea of spontaneous fission. Any nucleus whose z square upon a is greater than or equal to 4 to 444 would not be found on the earth for the simple reason that it would have undergone fission. Now that also answers the question as to why in nature there is an upper limit to the z value or a value of the elements which are found in nature. Why don't you have bigger elements existing in nature? They are not existing because this condition is satisfied and they would have undergone spontaneous fission long back. The time when the earth was formed, at that time, even if those elements were existing, they would have undergone spontaneous fission and they are not available now. So that's the reason why. And some of the elements which are available now are a good candidate for spontaneous fission. Now, who are the good candidates for spontaneous fission is the one whose gap between the Q and the potential barrier height is less. They are considered to be the good candidate, and that's the reason why the whole world is after uranium 235. In uranium 235, the gap is very less. You're talking about plutonium or you're talking about uranium 238. It's not a fissionable material because there is a 6 MeV gap in 238, while this gap is about 1 MeV in the case of this gap is 1 MeV in case of 235. So when you bombard neutron, you are able to overcome this barrier and then you are able to artificially undergo or implement or execute fission. So that's the whole idea. So that also answers a lot of question here. The smaller elements are not fissionable because for the simple reason that z square upon a is uh, such, the value is such that the gap, the potential barrier gap, this gap which I was again referring to, this gap here is very large. This gap is large. For smaller elements, this gap reduces as A increases. So the lighter elements are very difficult to undergo fission. But yes, but we had seen that any element of z square upon A is greater than or equal to 15 can be is a fissionable candidate, right? It can undergo fission, but it cannot happen spontaneously because of the barrier, right? Now let's see the transmission probability. Now let's attack this problem from probability tunneling. Just as you had alpha tunneling, now can we have the fission fragment tunneling? Now what stops the fission from tunneling? And if it is uranium 238, if you're talking about uranium 238, then uranium 238 would prefer emitting alpha particle rather than, you know that this is thorium 232 or 34, sorry. So we have seen this in alpha decay. Now uranium 238 would prefer emitting an alpha particle and converting itself into this rather than undergoing fission. Now what is it? Now what is the reason for that? Well, the reason is simple that the expression is the same. The probability of tunneling, the same expression I have taken it from the alpha decay. Please refer this expression. Okay, this is the product of the charge. This is the Coulomb term minus the energy possessed by the, this is the Q value, energy of the fission fragments, which is equal to the Q I have taken. So now this is product of the charges. So here you can see that ZE by 2 raised to half because the two fission fragments I am considering to be equal in size. So if Z is there, then this becomes, the charge would become Z by 2 into E. So the product of the charges is ZE by 2 square 4 pi epsilon 0 and divided by R. minus E. So here the whole idea is that this is this gap, that is the potential barrier height and the energy of the fission fragments. This term here we know from experiment that it is about 6 MeV. How do we know that? I told you in the previous lecture that when we bombard gamma rays of 6 MeV, we are able to undergo uranium 238 photofission of uranium 238. So the barrier height would be around 6 MeV. So if they consider this to be 6 MeV, and we are just taking an approximate case that if you take a rectangular top, just an approximation, and this is the barrier width, which you're talking about here is the barrier width. Now if you considering the barrier width of 8 fermion here, and that is the from the potential diagram, and the product of the charges here for fission fragments would be, if you divide 92 into 2 parts, it becomes 46 46. The product of the charges is 202 while in case of alpha particle it is 180. You know that it is a negative term, negative exponent. So smaller the better. If it is smaller, then the probability of tunneling is higher. If the exponent is very large, then the probability of tunneling is very high. There are two reasons here. If you can do the calculation, we have done the calculation for alpha decay. You know that the half life is around 10 raised to 8 or 10 raised to 9 years. And if it was similar calculation for uranium 238 against spontaneous fission, then it turns out to be 10 raised to 16 years. So it will take about 10 raised to 16 years for a probability of 10 raised to 16 years for uranium 238 to be undergoing fission on its own. Now, dear students, 10 raised to 16 years is too long a time. Our Earth is not more than 10 raised to 10 years. So we don't know what's going to happen after 10 raised to 6 years. And if at all the uranium 238 is going to be there existing, then there are chances that there could be explosion in any parts of the world wherever the uranium 238 exists, because there is a finite probability that it can undergo spontaneous fission, and the probability of course is very very high. We are not talking about ruling the probability, we are not telling that the probability is zero. The probability is there, but the probability that it might take place, that it might undergo fission, is very less, because the half-life is turning out to be 10 raised to 16 years. Now, how did we do the calculation? Of course, you don't have to do the calculation. I'm just trying to say how to calculate the calculate. This we have got Z upon 2. Okay. And what we have done is we have taken the formula for the rectangular top. B, we have taken it as 8 fermion. And the difference here is 6 MeV. And then the mass we have to take. You know that the I had asked this objective in CIA1 also. If the mass is very high, the probability of tunneling is also going to be less. So you're talking about massive objects you're trying to tunnel out compared to alpha particle. That's why uranium 238 would prefer to decay via the alpha route rather than the fission fragment route. And but having said that, uh, the probability is not zero. There is a finite probability which leads to a half-life of 10 raised to 16 years. So for alpha decay, the probability is 10 raised to 9 years, and for fission fragment, it is 10 raised to 16 years. Now, then finally, this leads to this question. This graph has been plotted. This is the half-life, and this is the z square upon a for various elements. You can see 10 raised to minus 14, 4 half-life. So you can see this is some element here. We don't even get to see them now because they want to go spontaneous fission. So as the value z square upon a, you can see that as z square upon a increases here, the half-life will decrease, and they don't decrease. And the stability limit, those elements which are above z square upon a, they don't exist on this earth. So that would be somewhere, somewhere here, somewhere here. So you can draw a cutoff that all these elements here would not be existing because they satisfy this limit. This is the explanation. So let me sum up the achievements of liquid drop model. So liquid drop model was developed, the mass formula was developed from the binding energy expression, and using the mass formula we try to answer various nuclear phenomena like stability of isobar family, and then we saw how successful it was there. Then we moved on to another success of liquid drop model, that is predicting the energy released in a fission. And then we also went on to see how the liquid drop model is able to predict the elements which are fissionable. So all those values whose q is greater than 0, and so that's z square upon a. We found out greater than or equal to 15 are fissionable. Then we moved on to the topic of spontaneous fission. Now, if they're fissionable, do they happen on its own or do they need external trigger? And then we found out that most of the elements, all the elements which are existing right now on the Earth, don't undergo spontaneous fission because of the potential barrier, and the potential barrier is different for different values of A. So then the next question is, which elements are stable against spontaneous fission? Using liquid drop model, we got the condition, which turned out to be 53, and then we refined that value because in nature the value is not 53 but around 44, and Bohr and Wheeler could give an explanation. They said that liquid drop, the nucleus is equated to a liquid drop, and just as the liquid drop is split into two droplets and it undergoes various shape transformation from spherical shape to ellipsoid to dumbbell and all that, a similar exercise could be done for a nucleus. So by doing that exercise, we found that the Coulomb and the surface term all got altered. So it depends upon the two values, and when the Coulomb term is able to overcome the surface term, in obviously the nucleus is uh, split, and because of the Coulomb repulsion, proton being positively charged, neutron is not charged at all, and that's what is the reason for fission. And then we finally discussed what is the half-life against spontaneous fission. If spontaneous fission is to happen or there is a probability, then what is the probability, and what that probability, from that probability we actually talked about the half-life. Then the half-life turned out to be very very high against spontaneous fission compared to for example, let's say alpha decay in case of uranium 238. So this has been a wonderful journey of the liquid drop model story, right from the time we discussed uh, the various features of stable nucleus existing in nature, then moving on to developing a mass formula, then the binding energy expression, and then refining the liquid drop model by adding the symmetric term and the pairing term, and then trying to answer all these questions which I just mentioned. Thank you. And we will be solving some numericals. I will be trying to give them in my next presentation.